Let's look at where we left off on the previous video. Now we're going to consider all those approaches to finding all the zeros of a polynomial function, finding both the real and the imaginary ones. So here are some steps that will help you in finding all the zeros. So first, we're going to go to our calculator. We're going to graph the function, and then we're going to use the Calc 0 feature or the table feature on our calculator to find those zeros first. So our first step is going to go to the calculator and find as many as we can on the calculator. Once I've gotten all that I can from the table feature or the Calc 0 feature, then I'm going to use repeated synthetic division to get the polynomial down to a quadratic. So I'm going to get what I can from the calculator, use synthetic division, get that polynomial down to a quadratic, and once you have it down to a quadratic, you're home free. You can always use the quadratic formula to find the last two zeros. So we're going to get started using, so we'll do our calculator, we'll then use synthetic division, and then we are going to finish up with the quadratic. All right, so how we're going to start? On the calculator. So here is our first problem. So let's go to the calculator and let's get that thing typed in. So let me go to y equals. You do the same with me. Minus x to the fourth plus 3x squared plus 4. So take a look at this polynomial function. How many zeros do you expect us to find? That degree right there tells me I am looking for 4 zeros. So 4 zeros in total. So let's go to our calculator. I like to go to the table first just to see if I can get anything from the table. Okay, so here is the table for the graph of negative x to the fourth plus 3x squared plus 4. So all I did was went to second graph and that gave me my table. And as I scroll along, I am finding 2 zeros. Remember when you got a 0 in the y position, that means you have found some zeros. So I got one at positive 2 and one at, positive 2 and negative 2. So it's a good idea to scroll through your x values to see where those zeros might be. Also, you could look at the graph. Take a look at the graph. There's an x-intercept, which is a 0. There's an x-intercept, which is a 0. And the table said 2 and negative 2, and that looks like where it's crossing. All right, so I am on my way to finding all 4 of my zeros. Notice I'm only getting 2 zeros from the graph, but there's still 2 zeros left to find. The other 2 are going to have to be imaginary. Let's look at finding that. So from the table, we see that positive and negative 2 are zeros. And when we look at the graph, we see that those are the only 2 zeros that we can find. So that means the remaining 2 zeros must be imaginary. So let's look back at our method. I've done my calculator. I've found the ones from my calculator. Now I need to use repeated synthetic division to get this thing down to a quadratic. It's a fourth power, and if I divide it twice, I will get it down to a quadratic. So let's put our box up. And in the box, we're going to put our zeros. So I'll start with the 2, and the coefficients are -1, 3. Nope. Got to remember to put those skipped terms. So that's a fourth power. I don't have a third power, so I need a 0. I have a second power, which is a 3 coefficient. I don't have a first power, but I do have a constant. So we've got to remember to put those missing terms in. So let's see, 2 times -1 is a -2. Add those up. 2 times -2, -4. Add those up. 2 times -1, -2. Add those up. 2 times -2, -4. Remainder of 0. We knew that was going to happen because we divided by a 0. So let's do repeated synthetic division. From that result, let's do our second synthetic division. So I'm going to drop that -1. -2 times -1 would be a 2. Add those up, I get 0. -2 times 0 is 0. Add those up, a -1. -2 times -1 is +2, and when I add those up, I get 0. I expect that because both of those were zeros. So remember, we're finding 4 in total by doing 2 repeated synthetic divisions. This quotient at the bottom is a quadratic. There's a 0 middle term, so it'll be a -1x² plus 0 minus 1. So actually, that would probably look better as just x² minus 1. There's my quadratic. -x² minus 1. Actually, let me do the whole thing here so you don't get confused. It's a -1x² plus 0x minus 1 equals 0. That's our quadratic. And I don't need the 0x in the middle, and I don't need the understood 1 in front, so I will just write it this way. -x² minus 1. It's a quadratic. I need to solve it. What's nice is I can use the square root method on this one. So I am going to take that 1 over, becomes a +1. I'm going to get rid of the negative in front of the x² by dividing by -1. Always want your square to be positive. And I'll finish it up with the square root of both sides. And when you square root both sides, you're going to get a plus or minus. And what is the square root of a -1? Well, if we go back here, we said the square root of a -1 is I, our imaginary unit. So what is the listing of my 4 zeros? Right here in the middle, let's just list them. I've got a 2, a -2, a positive I, and a negative I. Notice these imaginaries come in a pair, conjugate pairs. So we go to our calculator first, find as many as we can from the calculator, then do synthetic division to get it down to a quadratic, and that's where our quadratic was. So I want you to try this one. Pause the video and use the steps that I just used to find all the zeros. I'm gonna pause mine too while I work it. Well, did you put that in your calculator? I put it in my calculator and looked at my table, and here is my table on the right-hand side. I knew I was looking for 3 zeros because the degree is 3. And as I scrolled through my table, I got lucky. What do you mean? What do you mean, Miss Hardiman, you got lucky? Well, I found that 0. Oh, I found a second 0, and ta-da, I found a third 0. And how many was I looking for? 3. So I don't need to do any of my synthetic division. All 3 of my zeros came straight from the table. This doesn't happen all the time. It didn't happen in the previous problem. But if you can find them all from the calculator, hooray. The zeros for this function would be -3, -1, and 0. Okay, now I want you to pause the video and try the next one. Well, here's what I see for this function. Looking for 3 zeros, I went to my table and I found 1. Hey, at least I have 1. 1 from my table. So from my table, I've got a 0 of -3. But I know there's 3 zeros, and when I look at the graph, I see there's 1 here, 1 here, and 1 here. Why do the other ones not show up on my table? It's because they're irrational. What do I mean by irrational? These guys will end up with square roots, which probably tells me I'm going to need to use the quadratic formula. But I've got enough information. Remember, once you find what you can from the table, we do synthetic division to get it down to a quadratic, and we can use the quadratic formula to find the rest. So let's go to our box. Let's put in the 1 from the table, the -3. Let's write down our coefficients. We don't have any skipped powers. 3, 2, 1 constant. We should get a remainder of 0 because I'm dividing by a 0. And let's go through this procedure. All right, I lost a sign somewhere. Let me see. Drop down my 1, -3. -3, 7 plus a -3 is 4. -3 times 4 is -12, and that's a -1. That gives me a 3, and I have a remainder of 0. Now, I'm left with a quadratic. It was a 3rd degree. I divided it once, which brings it down to a 2nd degree. So that's x squared plus 4x minus 1 equals 0. This quadratic will not factor. So we're going to have to use the quadratic formula. And you can use the quadratic formula on those that do factor. So recalling the formula, all that divided by 2a. So negative b plus or minus the square root of b squared minus 4ac, that whole quantity divided by 2a. Why don't you pause it, try your luck with the quadratic formula, see what you get. So by using the quadratic formula, I've got all the steps here. I end up with a -4 plus or minus the square root of 20, all divided by 2. You've got to be careful with your arithmetic on the inside of that quadratic. The -4 times the 1 times the -1 have to be multiplied out first before you can take the 16 and subtract it. And so -4 times 1 times -1 is a +4. Now, unfortunately, we are not done at this point. We need to go farther, so we're not done. And I'm just going to take a little place here, a little spot over here, intervene on this problem, but let's take -4 plus or minus the square root of 20 over 2, and let's simplify it. All that means is there is a hidden square inside that square root of 20, and we want to reduce that radical. So 20 is the same thing as 4 times 5. And 4 is a perfect square, so that's why I chose to break 20 into 4 times 5. And when you're working with radicals, when you have a multiplication, you can split those numbers up. So I can take the square root of 4, which is a 2, and leave the 5 underneath. Finally, the last thing I can do with this is I can reduce it further only if these three positions that I'm circling have something in common. The -4, the 2 in front of the 5, and the 2 in the denominator. They all have a 2 in common, so I can divide each one of those out by 2. That's going to give me my final simplified result for those two zeros. So -4 divided by that 2, so I would have a -2 plus or minus the square root of 5. I can put a 1 at the bottom, but it's not necessary. So notice these guys did not come up on my table because they're not nice whole numbers. Only the -3 showed up in the table. So I have a total of 3 zeros. Let's just list them up here. For this problem, our zeros are -3. Then we had what? -2 plus the square root of 5, and then -2 minus the square root of 5. Remember, those guys that are irrational will always come in conjugate pairs because they come from a quadratic. And when you have a quadratic, you always have plus or minus in the middle. Okay, so that one's a little tricky. That was a good one. Why don't you pause it and work the next one? I know the paper's getting a little messy now, but I want to see if you got what I got with respect to your calculator. So I typed it in my calculator, I went to my table, and as I scrolled through, I only found 1 0, which was at 2. Then I looked at the graph, and I saw at 2, my graph is bouncing. Now remember, I'm looking for a total of 4 zeros. But my calculator is only giving me 1, and that is not enough to get this thing down to a quadratic. But here's the thing we need to remember. When the graph turns around on the x-axis, the multiplicity of the 0 is even. Remember, multiplicity means how many times it repeats. So if you see your graph bouncing on a 0, then it repeats at least 2 times. So I'm going to start this off by saying I have zeros of 2 and 2 again because it's repeating an even number of times. Then we'll see what happens with that after I do my repeated synthetic division. So I'm going to divide by 2. Okay, so my coefficients are a 1, a 0, a -6, a -8, and a 24. So 2, -2, -12, -24, and I get a 0. So I'm going to divide by 2 again to get it down to my quadratic, and it's getting a little iffy here. 2, 4, 8, 6, 12, 0. Yes. Okay. So that 2 repeats itself twice. I am now left with a quadratic, and I'm going to use the quadratic formula. So that quadratic is x squared plus 4x plus 6 equals 0. So negative 4 plus or minus the square root of b squared, which is 16, minus 4 times a, which is 1, times c, which is 6, all over 2a. Let me pause that. So I am seeing negative 4 plus or minus the square root of, you should get a negative 8 under that radical. And 2 times a should be 2 times 1, which is 2. Here's one of those that we need to do like we did above, reduce that radical, because 8 can be broken down. What does the negative under that radical tell you? You're going to have an imaginary number. So this is actually negative 4 plus or minus. That 8 is the same thing as 4 times 2. But I'm going to put an I right there because it was a negative. So I got to make sure that negative inside my radical comes out as an I. Negative 4 plus or minus that I, square root of 4 times the square root of 2. So I'm going to do the square root of 4, which gives me a 2, and leave that square root of 2 underneath because he's not a perfect square. And that's all over 2. This one's getting a little sticky, isn't it? Last thing we look for on these is to see if there's anything in these 3 positions that they have in common that I could divide out. And I notice that they're all divisible by 2. So let's see what this looks like when we clean it up 100%. Negative 4 divided by negative 2 will be negative 2 plus or minus 2 divided by 2 is 1, so it's just going to be an I with the square root of 2. Those are our other 2 zeros. Notice they're conjugates and it's imaginary. That's why they didn't show up on our graph. So if I had to list the zeros for this function, it would be 2, 2, and the other ones would be negative 2 plus I square root of 2 and negative 2 minus I square root of 2. That was a tough one. What I am going to do, I'm going to stop the video here. Actually, I'm going to tell you what the answers are to this problem. I want you to work on this one and see if you can get the solutions and then check your work. Okay, so here's the complete worked out version for this problem. We were asked to find the roots of that equation, and since it was a 3rd degree, we would be looking for 3 roots. Well, finding roots is the same thing as finding zeros. You go to your calculator, we look at the graph. I found a 0 from my table, and the 0 was 0.5, which is a half. That was my starting point, because if I know one of my zeros and the total is 3, I can get the last 2 from the resulting quadratic. So the resulting quadratic was 4x squared minus 4x minus 2. Here is my quadratic formula work, and right here would be my list of zeros. So you can compare your work to mine. Let's just wrap it up with some important connections. When you're solving polynomial equations, you're going to use the same techniques as solving polynomial functions. If you have an nth degree polynomial function, it will have exactly n zeros or n roots if we're working with an equation. And that happens when we count multiplicity and imaginary roots. This also means that if our polynomial is of degree n, it will have exactly n linear factors. Finally, imaginary roots will always occur, and irrational roots will always occur in conjugate pairs. 2 plus 5i and 2 minus 5i are conjugate pairs. Negative 3i and positive 3i are conjugate pairs. So let's think about all this stuff right here. And let's do some critical thinking. Suppose I have a polynomial function and they're telling me that one of his zeros is 3 plus the square root of 5. Could you state another zero of this function? Well, you should be able to, because irrational zeros such as this will always occur in conjugate pairs. So if 3 plus the square root of 5 is a 0, then I know that 3 minus the square root of 5 would also be a 0. So let's consider the next one. Suppose the polynomial function has a 0 of 1 minus 4i. Could you state another 0 of that function? Of course you could. We just saw that they occur in conjugate pairs, so a 0 of 1 minus 4i must have a pair of 1 plus 4i. Suppose we have a polynomial that has a 0 of negative 6i. What's going to be another 0 to that polynomial? Positive 6i, because of the conjugate pairs. Now let's think about this one. Is it possible to have a polynomial of degree 3? And remember, the degree tells you how many zeros. So is it possible to have a polynomial with 3 zeros given this list of zeros? 2, negative 2, and 3i. Yes or no? It's going to be a big no. Why is it a big no? Because if you're ever given an imaginary or an irrational root, you must know that he has to have a partner. He can't stand alone. So if they just tell me 3i is a 0, I have to infer that negative 3i is a 0 as well. His conjugate must be considered. So no, I can't have a polynomial of degree 3 with those zeros. What would the degree have to be? 1, 2, 3, 4 zeros, so it would have to be a 4th degree. Answer number 5 and 6. Pause it and see if you can answer those. So check your thinking on those two. Problem number 5, yes, it's possible to have a polynomial of degree 5 given those zeros, because we have to consider the conjugates, and that would give us a total of 5. Number 6, state the degree of the polynomial that had this list of zeros. Again, we have to consider the conjugates. Negative 4i has a conjugate, 2 minus 5i has a conjugate, so the degree would be 7 if I counted all my zeros. 1, 2, 3, 4, 5, 6, 7. All right, that wraps up section 3.4. As always, let me know if you have any questions. This was a nice section that sort of brought everything together. I hope you have success with this.